and then we're gonna, or 14.1, excuse me, and then we're gonna do 14.2, and then we're gonna be done for today. So a reminder that in this last section, we've been interested in finding the key features for these rational functions and then being able to use those key features to generate a graph. So let's say we have the function f of x equals x cubed plus 3x squared minus x minus 3. And we're looking for these key features like the vertical asymptotes, removal discontinuities, zeros, y-intercept, other asymptotes, all that good jazz, yada, yada, yada. What is the first thing I'd want to do? Well, I might want to do something before I do that. I'd want to factor, right? So, because if there's any reducing I could do, that could affect the vertical asymptote, right? So the denominator, obviously, well, that can't factor. So I would have been okay just starting by setting the denominator equal to 0. That would be all right. But let's factor the numerator anyways. Notice that has 4 terms. How do I factor a 4-term polynomial? Well, best case scenario. You would have done this last year in Algebra 2. Grouping, yeah, that's the name of the term. Excellent. So we're going to make 2 groups. I'm going to group 2 terms together. Reminder, when you do the grouping, you have to have a plus sign in between. From the first group, I can take out a greatest common factor of x cubed, or squared, excuse me. From the second group, I can take out a greatest common factor of -1. From there, the x plus 3's are the same, so those can act as a greatest common factor. So when I factor that out, I'm left with x squared minus 1. And hey, what do you notice about x squared minus 1? That factors also, right? X plus 1, x minus 1. So clearly here, nothing's going to reduce. That's fine. So as Nolan suggested, to find the vertical asymptotes, we'll just start by setting the denominator equal to 0 and solving. Well, whoo, that was a workout. What about the removal discontinuities? It's not setting the numerator equal to 0. That's the zeros. So those would be 3, 0, -1, 0, and then 1, 0. How do we find the removable discontinuities? Or what are the removable discontinuities? It's not has to do with the degrees either. It comes from the reducing that you're able to do. Did we do any reducing?
No.
No. So are there any rules of continuity? No, because you didn't reduce.
Yeah.
More often than not on the problems, that'll be the case. I don't know what I wrote there. None. Okay. Y-intercept, we'll do that next. What's that got to be?
That's x equals 0.
Okay. So what do I get then?
Undefined.
Great. So what should my y-intercept be? None, right? Notice that the vertical asymptote is at x equals 0. So that's eliminating the possibility of a y-intercept happening. That's okay. And then the last thing are the other asymptotes, right? So here's where we need to compare the degrees. We have a degree 3 over degree 1. So what are we going to have to do to find the asymptote here? If if the degree of the numerator is bigger than the degree of the denominator.
Set the numerator equal to 0.
Nope, that's define the zeros. Nope.
Add.
No. No. You divide. So you have to do the polynomial division here. Now, how am I going to do that polynomial division for x cubed plus 3x squared minus x minus 3 divided by x?
Can you do some
You could, although I think it's going to be easier if I do something else. Since the denominator is a monomial, I can just rewrite this fraction as like 4 things with common denominators, right? So the first 3 terms can all reduce. There's our quotient. So our asymptote's going to be quadratic. It's going to be y equals x squared plus 3x minus 1. All right, well, let's generate a graph now for this stuff because, well, that's kind of weird that I got a quadratic asymptote. So I'll draw in my asymptotes. So there's my vertical asymptote at x equals 0. 1, 2, 3, 1, -1. Okay. And then I need to graph my quadratic asymptote. How do I graph? What do I need to graph a quadratic? No, man, you can do it by hand. I mean, you could do it with a calculator. We're not going to. We're going to imagine if we had no calculator, someone walked by with a hammer and just went smash on the middle of our calculator, which I might do someday on a test, you know. Just walk by with a hammer and just smash your calculator right in front of you. You got to have the vertex. How do you find the vertex?
Put in vertex below.
Oof. Pass.
All is it negative b over a?
Negative b over 2a. And then to find the y, we'll just plug that in. So what do we get here then? I get 9 over 16 minus 9 over 4 minus 1. So that's going to be negative. Oh, come on, Kulik. Negative 27 over 16. 9 times 4 is 36. Minus 9 is, yeah, okay. So negative 27 over 16 minus 1 is going to be like negative 43 over 16, I think. Yuck. But really like negative 2 and 9/16. So a little over 2.5. Okay, there. Then I need a point on either side of the vertex. So let's pick, say, x equals 0. That's an easy one to do. And then I'm going to pick a point symmetric to that. So if I have 3/4, then I would need like negative 1.5, right? The reason I want to do that is because, well, y equals 0 is just negative 1. Should be really easy to see that. Negative 1.5 is going to give me the same y coordinate, because I know that a quadratic is symmetric about its vertex. So it just saves me a little bit of effort there by picking my x's that way. Do I have to pick my x's that way? No, man. But I get a free calculation. And boy, I like that. I don't have to do any extra hard thinking here. All right. So let's plot those other two parts. So I have negative 3/4 and then negative about 2.5. And then I have negative 1.5, negative 1. And then 0, negative 1. Oh my gosh, guys. What am I doing here? Should have been negative 3/0, not positive 3/0. Yikes! Oh, fiddlesticks. Look at what I did. What is the value for a in that quadratic? It's 1. That's a 2. That's a 2. That's a 2. That's going to be, see, that's 9/4 minus 9/2. So that's going to be negative 9/4 minus 1 is going to be negative 13/4. Well, that's a heck of a lot nicer. So that's like 3.25. All right. Let's go fix that stuff down here now. Oh, boogers. All right. Negative 1.5. I don't know what this is. That point's not supposed to be there. There. Negative 1, negative 3, positive 1. Then we're negative 1.5, 3, 1, 2, 3.25. So we're like there. 0, negative 1. And then that should be then negative 3. So there's my asymptote there. All right. So now I just need to kind of draw in the graph part because I got my asymptotes in here. Whew, finally. Made enough of a mess out of it. Sorry about that, guys. Didn't mean to do that. So I have to connect these two x-intercepts and follow the asymptotes. So it seems pretty clear to me that it would have to look like that. Where I'm following that vertical asymptote on the right, and then I got to follow the quadratic asymptote on the left. And then I have to go through this other x-intercept. So it seems pretty clear to me, without crossing any of my asymptotes, it would have to go like this. Right? Didn't have to do any calculator. Do I need anything over here? No, why not? That's the correct answer.
It's square.
Because that arrow is still going left and up. It's not going straight up. So it's going to keep going over and over and over. It's just like, I've stopped drawing it kind of thing. You know what I mean?
Yeah.
So that's the whole picture right there. Yay! If you don't make a bunch of stupid typos because you're dumb and half asleep, that problem's not so bad. I just made a mess out of it because I'm really tired today. Feels like Friday. Yeah. Anyways, let's do 14.2. All right. So let's talk about some methods to solve a rational equation. If I have one fraction equal to one fraction, what can I do in that situation? Remember that this is also known as a proportion. That helps jog your memory at all.
You can do the numerator first.
Yeah, we call this like cross multiplication is usually the term that we use for that. If I have one or more fraction equal to one or more fraction, what can I do here? Well, no, that just would be one fraction. If you have fraction times fraction, that's just one fraction.
Plus fraction.
Yeah. Okay, so you could make a common denominator and add the fractions. Okay. That would give us a proportion, because now we just have one fraction on each side, so then we could cross multiply. That's one thing you could do, sure. Let's revise this, because this is a little bit too strong. So if we just need to make a common denominator on each side, so like you could have a different common denominator on the left-hand side and a different common denominator on the right-hand side. The fact is that you end up with a proportion, so then you can cross multiply. Sorry about that. Let's be a little bit clearer there. What else could you do? Could make a common denominator for all the fractions. Then set the numerators equal to 0 and solve. And that's really the same thing as what I would recommend, which is clearing fractions, where we multiply both sides by the least common denominator and then solve the resulting and then solve the resulting polynomial. What thing do you have to remember regardless of which method you use? You solve a rational function, there's something you have to do at the very end, regardless of the method you use. Nope. You have to check something. You have to check for an extraneous solution, right? The answers you get could actually give you a 0 denominator in the original problem, because any of these methods you're using at some point resolve down to solving a polynomial. Now the solution to that polynomial might be the same location as one of the discontinuities in your rational equation. So you do have to check at the end for an extraneous solution. Now, of all these methods, the only one that I'm ever going to show you is clearing fractions. I think it's by far and away the easiest method to use. It's the most flexible. It has the least downsides. Almost always is it going to be at least the fastest, but it'll never be the worst. So I really just do that for everything. So let's run through some examples and then get out of Dodge. To be clear, though, you could use any of these methods. They would all be okay. And I would not mark it wrong if you did something that I wasn't really expecting, but was correct. All right. So let's say we have x plus 3 over x equals 4. If I look at the denominators, what denominators do I see?
1, 4, y.
Those are x's. Everything is an x. 1 and x, right? Good. So the least common denominator should be just x, right? So I'm going to multiply both sides by x. So I get x squared plus 3 equals 4x. The polynomial I'm left with is a quadratic. Great. To solve a quadratic, what should I do first?
Factor it.
Well, can I factor it the way it's written?
Subtract it over.
Yeah, it has to equal 0. Very good. And then you could solve this by factoring or
Reduce it.
the other way to solve a quadratic?
Quadratic formula.
The quadratic formula. Now, it doesn't really matter which one you use. In this case, factoring works. Does factoring always work?
No.
No. So there will be cases where you have to use a quadratic formula. This is not one of them. Let's factor this. How does x squared minus 4x plus 3 factor? x minus 3, x minus 1. I heard whispers from Isaac. Okay. So when I solve that, I get 3 and I get 1. But I'm not done here, right? What do I still need to do? Check to see if those right, check an extraneous. I'm looking to see if I plug 1 or 3 into the denominator, does it cause a 0? Well, no, right? Since the denominator is just x, clearly neither of these are going to make the denominator 0. So both those answers are good. They're keepers. So far, so good. You guys remember doing this last year? We usually do a pretty good job with this topic. All right. Next example, x minus 6 over x plus 1 equals 0. I'm going to multiply, I'm going to clear fractions. I'm multiplied by the least common denominator. What are the denominators present in the problem?
1 and x
And 1 and x plus 1. So the least common denominator should be? Yeah, 1 times x plus 1 or just x plus 1. Multiply that to both sides. So I have x times x plus 1 minus 6 equals 0. So x squared plus x minus 6 equals 0. Again, I'm left with a quadratic. To solve this, I could either factor or use the quadratic formula. I choose to factor because it's really pretty fast and easy. So I get negative 3 and positive 2. Again, I'm checking to see if either of those give me a 0 denominator. I have only one denominator present. Negative 3 plus 1 is not 0. 2 plus 1 is not 0. So both of those guys are keepers. So far, so good. I'll take your silence as, yeah, man, I'm good. Okay. So here I have 2x over x minus 1 plus 1 over x minus 3 equals 2 over x squared minus 4x plus 3. Again, I'm going to clear fraction, so I have to identify what the least common denominator is. To do that, what should I do first? Factor that out, right?
Yeah.
How does x squared minus 4x plus 3 factor?
X minus 1 times x.
Yep, sounds like you guys are just starting at opposite ends. I'm going to meet in the middle there. So the least common denominator would be, now that we've got it factored, what would the least common denominator be?
X minus 1 times x minus 3.
Yep. Everybody okay with this? Again, we've done this before, so I'm just kind of skating past some details. If you feel lost, speak up and say something. I can elaborate a little bit more, ask a follow-up question or whatever you need. But I'm just kind of assuming that this is okay since we've done this before. All right. 2x times x minus 3 plus 1 times x minus 1 is equal to 2. Everybody okay with how I simplified that down? Okay. If it's not, say something and I can include some more detail here or there, but I'm just going to kind of assume that everything is okay unless you tell me otherwise. So I'm left with a quadratic there. When I multiply it all out and get everything onto one side, I get 2x squared minus 5x minus 3 equal to 0. Again, to solve this, I'd either factor or use the quadratic formula. If I chose factoring, what's the catch here? Well, is it easy to tell if it would work or not? No, man, why not? The leading coefficient isn't 1, so the factoring's a little bit more complicated. As a result, anytime I see a leading coefficient of 1, I'm probably just going to use the quadratic formula anyways, because the long factoring takes about as much time as the quadratic formula, and I'm not even guaranteed that the long factoring is going to work. So I would just cut my losses and just apply the quadratic formula. In fact, anything that I try to factor, if I can't figure it out right away, I'll just quit and use the quadratic formula. It's not worth like grinding away at one of these things for like 10 minutes just to find out like, oh, I guess I couldn't have factored it. Just if you're stuck, use the quadratic formula. Just get it over with. Let's see, negative 5 squared is 25. Negative 4 times 2 times negative 3 is 24. 25 plus 24 is 49. The square root of 49 is 7. 5 plus 7 divided by 4 is 3. 5 minus 7 divided by 4 is negative 1/2. What happens when I check, though? Again, I'm checking in the denominators. Oops. If I use x equals 3, what do you notice? Yeah, it doesn't work, right? It gives me a 0 denominator. Negative 1/2, though, totally fine. We'll take that one. Still doing good? Okay. So we got 2.5 over x minus 3 plus 0.5 over x minus 1 equals x squared over x squared minus 4x plus 3. First thing I'd want to do. Yeah, so what should I do before I get that, though? Yeah. And I guess I didn't mention this last time we were able to do some factoring, but it is worth mentioning here. You should take a moment and just see if you can reduce any of these fractions. If you're able to do that, it makes the least common denominator potentially smaller, which will make the problem overall much easier. So it's worth taking just a second. Obviously, there's no reducing I could do on the previous problem. There's no reducing I can do here. But it is worth checking to see if there's any reducing you can do before you go plowing forward. Yes, sure. Of course. All right. Let's go find that least common denominator now. What would that least common denominator be? X minus 3 times x minus 1. Okay. When I distribute things through, I get 2.5 times x minus 1 plus 0.5 times x minus 3 equals x squared. And yuck! Look at these stupid decimals rattling around here. Do those look exciting to you? I'm not interested in that. Guess what I'm going to do to make this a little bit easier on myself? If I just, what? Multiply both sides by 2. Yeah, that'll do it. Now, do you have to do that? No, I just did it to make the arithmetic a little bit more convenient. So go ahead and distribute everything through and then move it all onto one side. And what do you notice here after I got it all on one side? Well, look at the coefficients even. Yeah, I can divide that all by 2. That makes life a little bit nicer, even if I'm going to use the quadratic formula, which I guess I have to, looking at the coefficients involved. But hey, I'd rather use the quadratic formula with those numbers as small as possible. It just makes the arithmetic that much easier on me. So I'm going to, not that I had to notice that or had to do it, but it was easy to do, and it makes my life a little bit simpler. So I'll take it. My life is complicated enough. All right, let's see. Oops. So I have 3 plus or minus 9 minus 16 is negative 7. Ooh, what's the square root of negative 7?
Plus I.
Yeah, you get an I there. Now, typically when we get this, rather than reporting a complex number as a solution, we'll just say like no real solution in this case. Not wrong if you left it as the complex answer, that would be fine, but my suspicion is in the answer keys, we just call these no real solutions. What do you guys think? So far, so good? Does this coming back seem familiar? You remember doing a fair amount of practice with this last year? I got one more example, but it's a story problem, and I don't want to write it down, so I'm just going to screen grab it and drop it in here. Bloop. All right, this says that Bill wants to fence off a rectangular pasture. His pasture must be 500 square feet. What is the smallest amount of fencing that Bill will need? So this is like a geometry, or at least a geometry-ish situation. So I'm going to start by drawing a picture. There's my pasture. I'm told the area of this pasture has to be 500 square feet. How did I know that 500 square feet was an area?
This is square.
Good, square feet, good. Since it's a rectangle, how do I calculate the area of this rectangle? Length times width, right? So I can say length times width equals 500. Now, what is it asking for? The amount of fencing, right? So it's looking for that. What is that going to equal?
That's squared. L squared.
The perimeter, 2L plus 2W. So what I'm going to do is I'm going to think about this as kind of a system of two equations. So I'm going to rewrite either L or W in terms of one variable. Or I'm going to rewrite that first equation, L times W equals 500, in terms of either L or W. So like L equals 500 over W. And then I'll make a substitution into the second equation. So what I have now is an equation for that perimeter in terms of widths. It's now asking me for the minimum amount of fencing. It wants the minimum value of that function. Algebraically, we don't have a good method of doing this yet. If you take calculus next year, we'll learn how to do something like that. It's not difficult, but you need calculus to do it. What we're going to do instead at this stage of the game is just rely on our calculator. So what I'm going to do is I'm just going to type this function into the y equals menu. And I'm just replacing the w's with x's. And the f is just going to be my y, my dependent variable. So there's that. I'm going to set myself a window. The width for this thing, I don't know, what's the maximum width you can get? It's probably infinitely big, but let's just say like 500. Maybe if this is 500 by 1 rectangle, that could still give me the right area. Go by 50s or something. And the amount of fencing, well, if that's 500 by 1, that's 1,002 feet of fencing. I'm pretty sure that's going to be not the optimal, but I'm just looking for like a big upper bound or something there. So that seems like good enough. Let's just hit graph. So here's my function. Look, there's the minimum right down there, right? The lowest spot on that function. How do I find that with my calculator? How do I find what that point is? Second, trace to open up the calculate menu. And which of these commands do I want? The minimum command, that's right. So the minimum command asks for three things: a left bound, a right bound, and a guess. So in my infinite wisdom, in this cool window I picked, where that minimum actually is visually is covered by the question. So to move my cursor on the left side of that, I'm just going to be looking at the y value and waiting for that to stop going down. So as I go left, it's continuing to go down. As soon as that number starts getting bigger again, I'll know that I'm on the left side of that. So there, it started getting bigger again, so that's a good spot. I'll just press enter. Now it asks for right bound, so it's going to start getting smaller as I go back to the right. So again, when it starts getting bigger again, the y value, I know I'll be over on the other side. There it goes. Press enter, and then a guess is fine wherever it's at. So there's the answer. The width should be 22.36. And the height, or the fencing should be 89 and change there. And this is the answer, because that's the amount of fencing. That's the perimeter. How do you guys feel? It's all right? Okay. That's all I want to do today. So at this point, you guys should now be able to do like 25 to 34. Last time I assigned 1 to 24. That's what's going to be due here this Sunday. And this stuff will be due the following Sunday, plus some stuff that we do next week or whatever. And at this point, you guys should get your stuff out and start working on your problem set. With any luck, you can finish a big chunk of 1 through 24 if you haven't started, or if you have started already, maybe finish it up to have your weekend free and clear of mathematics. I know that I'm ready for a nap already today. I can't imagine I want to have my weekend bogged down with grinding through a whole mess of math problems all in one sitting. I'd rather get some done now and give myself some time to watch an NBA basketball playoff game or something. You know, some hoops.